So we're going to take a look at factoring higher degree polynomial functions here. Many of the usual factoring methods, like the AC method or the difference of squares, these things tend to be based on a second degree polynomial, and because it is a second degree, it's a smaller degree, there's fewer things to worry about, fewer factors really. So when we're dealing with higher degree polynomials, we can have potentially more terms and definitely more factors overall, so it can get a little bit tricky to work with. So we're going to start with, first of all, the most basic of all factoring methods, the first factoring method that should ever be attempted, factoring out the greatest common factor, or GCF. This is the simplest by far, and also often the most helpful, because if there is a common factor, sometimes taking it out changes the nature of the polynomial by changing the coefficients or even changing the degree. For example, suppose we have 10x cubed plus 2x squared minus 36x. Somewhat of an intimidating polynomial, certainly, but we can note that each term has some number of factors of x in it, at least one. Some of them have more than that, but there's at least one factor of x in each term. Likewise, if we look at the coefficients, they're all even numbers. The 2 there, we can divide each of those things by 2. So what we are looking at here is that each term can be divided by 2 and by a factor of x. The idea is that each term has a certain number of factors in it. Like, for example, 10x cubed can be written as 2 times 5 for the 10 times x times x times x. So what we're doing is we're going to be removing the 2 and one of the x's and seeing what factors we're left with. But whatever we take out of the 1, we need to be able to take out of each of the others as well. So since we can't take anything more than a 2 out of this, that's the most we can take out of any of them. And since we can only take a single x out of this, that's the most we can take out of anything. So when we do factor out the GCF, we write it out in front, and then we take what remains from each term and put it in a set of parentheses. So 10 divided by 2 is 5, and if we have x cubed and we remove an x, that leaves us with x squared. So kind of as I already said over here, if we take the 2 and one of the x's out, what are we left with? 5x squared. Now in this case, we're taking the 2 out entirely, so we're left with a coefficient of just 1, which we don't have to write. And we have 2 x's, we're taking 1 out, it leaves us with a single x. Now you can write the 1 in front of that if you wish. It's not typically written, but it doesn't hurt to write it there if it helps you. Next up we have negative 36 divided by 2 is negative 18. And in this case, there's only one x, and we're removing it. So there's no x's in the result. And what we have is now this, which first of all should look like a distributive property style problem because, well, that's what factoring is. It's literally unmultiplying. It's saying what did it look like before it was multiplied. And that's why we have to take the same thing out of each one, because under the distributive property we'd multiply 2x to each one of them. So since it's the reverse procedure, we have to take out the same thing from each. Now, going back to the original question of higher degree polynomials, you'll notice that once that 2 and that x are out of the way, each of the coefficients is now smaller than it was before, which is a good thing in factoring. It usually makes it easier to deal with. And, more importantly, the degree went from a third degree polynomial down to a second degree polynomial because we took one of the factors of x out. And now this we can factor by the more typical means, in this case the AC method, which we're not going to get into here, but the idea is that the GCF gives us a way to reduce the degree. Not always, but often. Now, sometimes a higher degree polynomial has more terms, and that's where the grouping method can sometimes be employed. The grouping method is based on the idea that while there may not be a common factor among the entire polynomial, there might be if we only consider it a couple terms at a time. So, for example, (4x cubed plus 10x squared plus 2x plus 5). Now certainly if we look at all this, this has no x's at all. That prevents us from taking an x out of the entire polynomial. And there's no common factor among all four of the coefficients. I'm sure each of these is even and can be divided by 2, but this is a 5. 5 is a prime number. It can only be divided by 5, or by 1, but that would be silly. So this can only be divided by 5, but this one can't. This can only be divided by 2, but this one can't. So we don't have a common factor among all of these. But if we kind of separate it here and look only at the first two terms, those two terms have something in common. If nothing else, because of the degrees of the terms, they have to have x's in common. They do happen to also have a common factor in the coefficient. In this case, both the 4 and the 10 can be divided by 2, and both terms have at least 2 x's. So we can take out a factor of 2 and 2 factors of x. Now, like when we did the GCF before, we write that in front, and in parentheses, we write next to it what's left over. 4 divided by 2 is 2. And if we remove 2 of the x's, we should be left with a single x. In this case, all of the x's are removed, and 10 divided by 2 is 5. We can then do something similar with the second group. Now, in this case, we did actually already kind of point this out before. They don't both have an x, so we can't take out an x. This can only be divided by 5, but that doesn't work on the 2x. And the 2 can only be divided by 2, but that doesn't work on the 5. Sometimes there just is no common factor. So that might leave you the question of, what are you to do? Well, part of the idea of the grouping method is that when you're done with it, it's supposed to have the leftover terms in the parentheses here, and then if this is going to work, it should have the exact same expression in the second set of parentheses from this pair, which actually is exactly what's already there. That works out perfectly with the idea that there was nothing to take out. Well, there's always something to take out, even if it's a silly thing like a 1, which of course doesn't do anything except kind of hold the place, which in this case is important because there is one more step. The next step is to do a common factor again, but this time the common factor is the polynomial factor. So I'm going to remove the 2x plus 5 from each of these. Excuse me, 2x, not 2x squared. The 2x plus 5 from each of these, and it leaves me with 2x squared plus 1. That's why that 1 is important to write there. It leaves us with 2x squared plus 1. Now, the grouping method is great. It actually gives the foundation for the AC method even. However, it is limited. The requirements for the grouping method are that you have to be able to separate the polynomial, the terms of the polynomial, into equal size groups, because you need to have identical polynomial factors here. The only way they can be identical is if they start with the same number of terms. So you have to have, say, in this case, 2 terms here and 2 terms here. Though if it is a higher degree polynomial still, like say it's degree 5, and it can have up to 6 terms, well, then we could do a group of 3 and a second group of 3. Or, if we really wanted to be creative, we could do a group of 2 terms, a second group of 2 terms, and even a third group of 2 terms. So we can break it up however we want. The important thing is that however many groups there are, they all need to have the same number of terms. And when we do factor out a common factor from each group, it has to leave the same polynomial factor in parentheses next to each one.